It's because your body's not used to it, being around all this. Yeah. I was sick the first work week when we were in here. How about your homework questions about that? Yeah, so I started. Are you talking about the back side or the front side? Second page. I got 5 for A, 5/3 for B, 5 for C, 1 for D, 1 for E, and that's as far as I got. Yes. And C? All right, so C is the limit. I think all of these were algebraic. The limit as x approaches 1, and I have 7x squared minus 4x minus 3 over 3x squared minus 4x plus 1. So you can't plug the 1 in, right? You'll get 0 in the bottom. Is that right? So I factored. What multiplies to negative 21x squared but adds to negative 4x? Negative 7, positive 3. And on the bottom, multiplies to 3, adds to negative 4, so negative 3 and negative 1. 7x, x minus 1, 3x minus 1 over x squared minus 1. Getting ahead of my 3x, x minus 1, minus 1, x minus 1. You might have already seen it at this point before you. So now I can get rid of that discontinuity. I can remove it. So I end up with 7x plus 3. The limit as x goes to 1 of 7x over 3x minus 1. And now I can plug that 1 in. And I get 7 plus 3 over 3 minus 1. 10 over 2, which is 5. A whole lot of algebra. 5 and 5/3. Same thing. And then you said D. Limit as x goes to negative 2 of x to the 4th plus 5x cubed plus you cold. X squared, x plus 1, 4x plus 1. All right. I'm just going to work with this a little bit. I'm going to take x squared out of the top, x squared plus 5x plus 6. This is already grouped for me partially. So I got x plus 1, x squared minus 4. I'm going to shortcut factor this. Multiplies to 6 but adds to 5 would be 2 and 3, right? There's a leading coefficient of 1, so I don't have to go through all the grouping. I can do x plus 2, x plus 3, x plus 1. This is a difference of 2 squares, x minus 2, x plus 2. Remove that discontinuity, and now I'm going to negative 2. See if I can plug in now. Hopefully I can. X squared, x plus 3, x plus 1, x minus 2. Negative 2 squared would be 4. Negative 2 plus 3 is 1. Negative 2 plus 1 is negative 1. Negative 2 minus 2 would be negative 4. And I end up with 4 over 4, which is all that work to get 1. Okay, we'll look at it. Is that when it started? I feel like it was, yeah. Let's see. Oof. Y'all tired today? Y'all seem pretty bleh. Alright, I'm gonna do. Oh, it looks like I don't. No, that's a different one. The square root of x plus 1 minus 2 divided by x squared minus 9. Is that what y'all got? Did it do that? Okay. Square root of x plus 1 minus 2, all that's on the top, divided by x squared minus 9. That's not what y'all's look like? Let me zoom in some. There we go. Regardless, I'm approaching 3. Clearly, I'm not going to be able to see it from the graph, so I'm going to go into the table. 2.9, 2.99, 2.999, 2.99999, and I'm going to come in the other way, 3.01, 3.001, 3.0001. It looks like I'm getting closer and closer to this 0.04 number. So I would say that would be a good estimate. It says the limit as x approaches 3. I would say no on the exam just because you got to go out 3 places. I would say 0 for, let's see, 2. It looks like it's getting closer and closer to 2. 0 for 2. That would be my best estimate based on a table. Did anybody do it any differently? I don't see anything there you could do algebraically. And then what happened? You sure about that? What, 0 on the bottom when you plugged it in? That's a difference of 2 squares. So x minus 3, x plus 3. If you plug it in, you end up with a 0 here, which is a 0. Yeah. I'm going to say that that's an asymptote there, a non-removable. I can't find anything to cancel it out to remove it with. That one was tough. What else? G. G, the limit as x approaches 3, the square root of x squared plus 7 minus 3 over x plus 3. I would substitute here. If that was a negative 3, I couldn't substitute, but because it's positive 3, I would just say, well, that's the square root of 9 plus 7 minus 3 over 6. Is that what happens when you graph it too? It's not too different. It's the positive root. It's not. It doesn't do anything with the negative one. See what I'm saying? Graph it and look at it. Well, because technically when you take the square root, that could be plus or minus 4, right? Normally we stay with the primary root, but I just want to make sure there's not another. No, that's good. Say again? You usually just take the primary root there, yeah. So what I did was I graphed it to look at it just to make sure there wasn't some type of asymptote or something there, that it was going in two different directions, but it's not. 1/6, yeah. What else? J. Y'all didn't like these too much, did you? Well, why didn't you sub in this one? Why'd you put it in the calculator? Yeah. What's the cosine of 0? 2 times 1 minus 5. It'd be a negative, so what does that tell me? It does not exist. Yeah. Does not exist. K and L. Ooh, I like K and L. Those are complex fractions. The limit as x goes to 0. I've got 1 over 3 plus x minus 1 over 3 minus x over x. I'm going to go ahead and multiply by x on the 1 over x here. Well, maybe I'll combine the top first. If I think about a common denominator here, right? Common denominator would be 3 plus x, 3 minus x. We all agree? Don't worry about the x on the bottom right now. We'll come back to it. So this one needs a 3 minus x. This one needs a 3 plus x. So that would put them both over that LCD. And now I can combine the tops. So I would have 3 minus x minus 3 plus x over 3 plus x. Oops. Y'all okay there? I don't know what that's going to do for me, but I'm fixing to find out. 3 minus 3 is nothing. Negative x, so I got negative 2x over 3 plus x, 3 minus x. And now, yes, I can multiply by the reciprocal here, which is 1 over x. Well, it's negative x minus x. Because I got to keep that in parentheses. Now I see why they had it set up like that. Right, those x's are gone. So I end up with negative 2 over, remember what I told y'all in the beginning? It's always the algebra that gets you. We haven't done any calculus with it yet. Now we'll do the calculus. What's the limit as x goes to 0 of this? Negative 2 over 9. Multiply. Negative 2, 9. That's thinking algebraic manipulation. Every time. So think about how you find the least common denominator, right? If I had 1/3 plus 1/2, to find a common denominator, even if it's not the least common denominator, I can multiply these two together, right? So here, I just did the same thing, only it's 3 plus x and 3 minus x. Those were my two denominators, and I gave it to the top and the bottom. What else? Y'all asked for another one. The one after that. L. The limit as x approaches -6 of 2x plus 8 over x squared minus 12 minus 1 over x over x plus 6. Again with the LCD here. I'm going to focus on this one. I'm going to give this one an x. I'm going to give this one an x squared minus 12. Top and bottom, right? X squared minus 12. Now combine your numerators. Caroline, you look like you're fixing to fall asleep. X times 2x plus 8 minus x squared minus 12 over. Is that confusing to y'all? Do y'all see what we did? Yes, it's confusing, or yes, you got it. It's not, okay. You sure? You can. That's essentially, that's a common denominator. It may not always be the least common denominator, but it is a common denominator. So if you ever get thrown off, when we did it in algebra 2, did we get to complex fractions in algebra 2 or pre-cal at least, right? Did we? Where we said do the top, then do the bottom, then do top times flip of the bottom. Y'all remember that? And do y'all remember that? No, some of you are like, yes, some of that. Okay, yes, then do that. All right, I'm going to clean it up a little bit. So up top, this is already factored. You really want it completely factored. This is not completely factored because of this minus sign. Remember, if it's not enclosed in a parenthesis, can't start canceling things out. And essentially that's what I want to do, is be able to cancel things out. So I'm going to have to make it messier before I can make it neater. So I'm going to distribute 2x squared plus 8x minus x squared plus 12. I'm still over this same bottom. 2x squared minus x squared would be x squared. I'm going to bet that this will factor. In fact, 6 and 2. So I've got x plus 6, x plus 2 over, again, this is all the algebra. I haven't done any calculus with it yet. Now I'm going to multiply by 1 over x plus 6. That's coming from here. And look at there. I bet that was enough to plug my hole. Because that original problem, it was divided by x plus 6. Everything I had done up until here, I was just working with the top. What am I approaching? -6? Isn't it still what? Well, I'm not going, it's the limit as x approaches -6. Now it'll be x plus 2 over x times x squared minus 12. So I won't have a 0 on the bottom anymore. It's not going to 0, it's going to -6. Where? That's coming from that original problem. Then plug in, right. So you'd have -4 over 36 minus 12 would be 24. One over 36. That makes sense? It's a lot of algebraic manipulation. The better you get with this kind of stuff, the better you'll do on the test and all, because this is where everybody gets bogged down. The hairpin drop. Preston, did y'all do complex fractions and That's just my little quick mental math. I simplified 4 over 24 first to 1 over 6, and then multiplied by the 6 that was down there. But you can use your calculator if you want to. 6 times 24 is, what is it? Avery, 144 is over 7. And 4 divided by 144 is 1 over 36. Put it on your calculator. Is that what it is? Okay. I'm always surprised at the little mental math tricks that they don't teach y'all in lower level anymore. Y'all good on that one? Okay. Abby, you okay? You look tired too. What else? Don't be scared to ask. 7. Answer the following questions for the piecewise defined function. Did this take y'all forever? C on 6. Okay, well, let me do that one first. And number 5. Okay, let's start with number 4. Number 4, find the following limits involving absolute values. So these are going to be calculator problems because I can't plug into any of these. Yeah, so I'll put them on the calculator. So let's put them on the calculator and see what they look like. Table or graph, it really doesn't matter. All right, let's do the first one. Let's do y equals. Be careful as you input and make sure you get your parentheses right. Ooh. I promise my fingernails aren't dirty, y'all. I was mixing ice and colors last night. I can't get the dye out from under. I'm at absolute value. And I'm approaching 1. Oh. So I wonder if it's defined there or if that's an asymptote type jump. Or if it's, does y'all show that little line? Yeah, I think my calculator tends to do that. If you have an older calculator like this, it will tend to do that. So if yours does this and you need to know, just go into your table, do what we've been doing. What am I approaching? 1.9, 0.999, 0.99999. Looks like it's getting closer and closer to -2 here. But what about this side? So what do I know about that limit? It doesn't exist. Because from one side it's approaching -2, from the other side it's approaching +2. So that limit does not exist. Does that make sense why? Sure. All right, let's look at the same. Right. The left-hand limit and the right-hand limit are different. All right, let's see. Let's do 1 divided by the absolute value of. You can hear Miss Hutto teaching. Squared. And what am I going to? -2. This little problem area over here. I need to see a little bit more up top. Take my y max up. 20, see what happens. I'm thinking this one probably does not exist either. But we'll check the table. -2.01, -2.001, -2.001. That looks like I'm going to infinity. And then from the other direction, so -1.9, -1.9999, -1. Oh, maybe I'm. You what? I think they are both going to infinity. So therefore that limit would be going to infinity. Yeah, go second graph. Oh, yeah. So you'll want to put the whole fraction in parentheses. That way you can add the x squared at the end and it doesn't tack it onto the denominator. Oh, I don't know why that's there. I'm sorry this was hard for y'all. I didn't anticipate it being so hard, but that's okay. Did it work? See how it's getting, the closer I get to 2, these numbers are just getting really, really big, or -2. And then I even came in the other way. I came in from both ways, and it's doing the same thing from both directions. And then part C, same thing, x squared, absolute value, x minus 3, divided by. I'm coming into 3 from the left. This one I can almost see. I think it's going to be negative infinity. But I'll check my table just in case. Since I'm coming from the left, I need to start at like 2.9, 2.99, 2.999. But I think it's going to be negative infinity. Maybe it's not. Oh, it's not. I didn't take it down far enough. So I guess going to -9. I'm going to assume if I adjusted my window some, I would see that. Well, 3.1 is going to be on this side of 3. Yeah. There's why. That's not actually an asymptote. It stops there. -9. I'm getting closer and closer to -9. And I'm only coming in from the left side, so I don't have to worry about anything else. Does that make sense? Y'all said number 5. Number 5 is a great one. And the reason number 5 is a great one is this is a typical, this was probably copied from a freaking multiple choice question. So it says, find the value of the parameter k to make the following limit exist and be finite. What then is the value of 5? I've got x squared plus kx minus 20 over x minus 5. So what they want you to see is that clearly at 5 I'm undefined here, right? I need it to be a removable asymptote. So what I need to do is I need the top to have some factor of x minus 5 so that this will cancel. Well, is there anything that I can plug in for this k so that this is factorable? I don't know what I could put here. That's a 20. The k would be -1. So x squared minus x minus 20 would work. Oops. Sorry. But do you see what we did? Okay, so what we're trying to do is make it so that this factor cancels out. So what would you need? What would you need for k to be in order for it to factor? So what they did was they looked at, well, I got -20, right? What 5 times what gives you 20? 4. How can I use that to add together to make a k? So k would be -1, and then the limit would be 3. if I put a 1 in, right? No, it goes to 5. 9. Sorry. Those get so confusing. What else? The next one. Answer the following questions for the piecewise function defined as described on the right-hand side. All right, so we have f of x. Get a little bit harder as you go. Sine of pi x when x is less than 1, 2 to the x squared when x is greater. What is f of 1? Y. Good job. That's exactly right. It's not greater than or equal to. It's just both of them are less than or greater than, so it does not exist. How about the limit as you approach 0? Which one do you use? The top one. So it would be the sine of 0, which is 0. How about the limit as x approaches 1? What do you do? Why? They're different. So you had to find what? Both left-hand limit and right-hand limit. The only way that limit exists is if the left-hand limit and the right-hand limit are the same. So what I'd have to do is say, okay, well, the limit as x approaches 1 from the left, I'm using this one, would be sine of pi, which is, what's the sine of pi? 0, thank you. And then the limit as x approaches 1 from the right would be 2 to the first power, which is 2. Therefore, since those do not equal, the limit as x approaches 1 of f of x does not exist. Yes, yes. So at pi, that's at 180 degrees straight across, so you have no height there. Because sine is your y value. Okay. 7? Okay. Well, this was a little more than I had anticipated. I apologize. Any particular one? Or you want me to just run through them? Okay, f of negative 3/2, so that's negative 1.5. Which one do I use? Ah, you are right. Yeah, it's not defined there. Definitely not a continuous function. How about f of 2? Which one do you use? Yay! The bottom one, 3 times 2 minus 2, which is 4. How about f of 3/2, so 1.5? The middle one, that's exactly right. So that would be 3/2 plus 6 over 3/2. I don't even know what you would get here. 9/4. Oh, let's see. I would do. Did y'all do a stow on your calculator? Yay, y'all! I would too. X plus 6 divided by x squared. 10. Is that what y'all got? How about the limit as x approaches negative 2? So I can plug into that t squared, right? And because I know that a quadratic is a continuous function, right? It's not going to be the same, so I can just plug in and say it's 4. I'm looking at this and thinking about what I know about a quadratic, what I know about that function. That function is just going to do this. The limit's going to be the same from the left and the right, so I can assume a substitution is going to work there. And I'm doing that because it's not or equal to, right? If it was or equal to, it'd be an easy substitution, but I had to think about it just a little bit and make sure I didn't have something different from the left and the right. How about the limit as x approaches, t approaches, just kidding, negative 1 from the right? What are you doing? Which one are you using? I can plug in this middle one because that's negative 1 from the right, which goes towards the positive side, right? No. Yes. Yes. Which would be in this inequality. So I can plug in there. So negative 1 plus 6 over negative 1 squared minus negative 1, which would be 5 over 2. Is that what y'all said? How about the limit as t approaches 2? What'd you do? And which one? Both of them. You're exactly right. Why both of them? I got to check left and right. So I'd have to do 2 from the left and 2 from the right and make sure that they're the same thing. So I'd have to do from the left, which would be 8 over 4 minus 2 is 2. I got 4, and then I'd need to do the right, which would be 3 times 2, which is 6. Oh, yeah, 4. Therefore, the limit as x approaches 2 of f of t is 4. How about the limit as x approaches 0? It would go in the middle one. How do y'all know it doesn't exist? Did you try to factor it? T times t minus 1. Did you look at it on the calculator? I do have a... We need to look at it and make sure x plus 6 divided by... What am I approaching? 0? Looks like as I come in from the left, I'm approaching negative infinity. And as I come in from the right, positive infinity, so it doesn't exist. But definitely check those and make sure. One's going to negative infinity, one's going to positive infinity, so it does not exist. You should get undefined if you plug it in, yeah. Because if you put a 0 in here, you get 0 on the bottom. So remember those, whenever I have that 0 in the bottom, I need to check it. First I try to see if it's a removable discontinuity that I can remove. If it's not, then I need to graph it and check for asymptotes, because if it approaches that same value on both sides, then that limit does exist. But if it approaches two different things, then it doesn't. Y'all need a break? Take a couple minutes. Tell somebody what it meant to be a continuous function. Tell me what you tell them. Never ending? Keep going. Tell me something else about it. No holes? Okay, so you'd never have to pick your pencil up. I think that's how we, okay, so I'm going to say pre-cal. Never lift your pencil. No holes or asymptotes. Right? But we're going to learn a little bit more sophisticated way to describe continuity in calculus. And we're going to use limits to do it. I know. So let's talk about some types of discontinuities and how we might describe them using limits. And then that will help us come up with our continuity definition. Tell me one type of discontinuity that you know. We just named two. A hole. Sometimes we call this a removable discontinuity. So it might look something like this, and maybe we plug the hole up here with something else. Let's call this value C. Tell me as I look at this, what is the limit? We'll call that C, and we'll call this H. It doesn't matter. Why I can't think of a random letter is beyond me. What is the limit as I approach C from the left? We'll call this H. How about from the right? So do you agree then that the limit as I approach C is H? What is f of C though? Do you see that the left-hand limit, the right-hand limit, the limit exists, it's the same, but the function defined is different there. Okay. How about another type of discontinuity? I should write this on here so you have it in your notes. The limit as x approaches C from the left equals the limit as x approaches C from the right. It equals the limit as x approaches C of f of x, but it does not equal f of C. That's the key there. The other one you told me, so this is a removable. Let's talk about non-removables. You said an asymptote, which we will also call, what type of discontinuity do we call an asymptote? Non-removable, we call it an infinite discontinuity. Continuity. Non. let's just use using random variables because that's the way they do in your. We'll call this C. Are we going too fast? Okay. What is the limit as I go to C from the left? Negative infinity. How about the limit as I approach C from the right? So notice on this one, these two do not equal, right? So the limit as I approach C does not exist on this one. That's another clue about my discontinuity. Can you think of another kind of discontinuity? There are 4, by the way, altogether. You've named 2 of them. What's that called? The little steps, you're right. It is a piecewise, but it's called something. Let me draw it for you and see. It doesn't even have to look like that. It could look something like. Yes, it's a jump discontinuity. Jumps from one value to the next. It's non-removable. Remember, that just means that algebraically I can't remove it from the equation. Just like with the removable discontinuity, the limit as x approaches C from the left, in this case, what is it? A. And the limit as x approaches C from the right are not the same. They're different. But if I do plug in sometimes on this, if I plug that value in, that f of C, it does equal one of those limit values. That happens sometimes. Sometimes this could, or maybe does not exist. This is enough right here when these don't equal to tell me that, hey, I'm not continuous. If the limit's not the same coming in from both sides, there's no way I can be continuous. I have one more that we haven't really talked about a whole lot. I'm not sure that we talked about it a lot even in pre-cal. But we've seen it in here a couple times already. You might know what it's called. You say sign. Oh, the slant. No. This is an oscillating discontinuity. It's non-removable still. But remember that one we did that did this, and the closer we got, it started doing this inside? Y'all remember that or no? More we zoomed in, the more it just started doing that number. Remember that one? It's called an oscillating discontinuity. We don't describe it with limits a whole lot. The limits would not exist as you try to find the limit as you zoom in. All right, so there's our types of discontinuity. No, this would be something like sine of 1 over x. It literally, you can't find a limit to approach a number because it keeps oscillating between things even as you get more minute. Mm-hmm. Smaller, but it just fluctuates between the two as you go in. It's really complicated. It's hard. They're hard. We don't do a lot with them other than to recognize that they are a discontinuity and it's an oscillating discontinuity. And other than that, in AB, we don't do a whole lot with it. All right, so in order to show or to prove, and you get asked this all the time, in order for a function to be continuous, in calculus definition. Now it's not just can I draw it without lifting up my pencil. Now it has to meet 3 criteria. Definition, yes, sorry. I'm not jumping my head. The limit, okay, so if I have f of x, your limit as you approach some value c has to equal the limit from the right, from the left, and it has to also equal the value at that particular point. Okay, so this has to be for all values on your domain. If it doesn't, then that's your point of discontinuity is C. Yeah. So let's look at a couple examples. This is number 2 on your homework. Find the points of discontinuity of the function and identify the type of discontinuity. So remember, I'm looking for holes, asymptotes, jumps. When are your jumps going to happen, by the way? Piecewise functions. That's exactly right. Your jumps are going to happen in piecewise functions, unless I'm in something like an integer function, but that's really the only one. But let's look at this one. Any ideas? Bottom. So let's see. If I factor that bottom, minus 3, x minus 1, I know I have vertical asymptotes where? 1 and 3. At x equals 3 and at x equals 1. Those are my discontinuities. They're infinite, right? I have 2 infinite discontinuities at x equals 3 and x equals 1. And that's all they asked me, right? Yeah. Does that make sense? And remember, notice that definition was for all values in your domain. So if you have something that's a domain restricted function, like a radical, you're only looking at those points in its domain, so it's still continuous. Does that make sense? Because a square root graph, remember, starts here, and it would look like, remember, it's the limit as you approach from the left and the right, but you have to look at just the points on its domain, so that one is continuous. Because you don't test points over here because that's not in its domain, even though it doesn't go on forever this way. Say again. This one's, it has y equals 0 is the horizontal asymptote. But that's not going to impact my continuity there for this one. Bottom heavy. So top heavy is none, bottom heavy is 0, and then the same as the. Look at this one. You try this one. You may have to graph it. This is a calculator problem. What do you think's happening? A jump. How do you know it's a jump? Did you graph it? Look at it. Does it make sense to you why that's a jump with that absolute value? So it looks something like this. So the limit as I go to, because you might be tempted to say this has a vertical asymptote at 0, right? But the problem is that absolute value up top. So that's a little bit different. Remember, the top equaling to 0 gives me my zeros of the function. The bottom equaling to 0 are my discontinuities or my vertical asymptotes, that kind of thing a lot of times. It's where I'm undefined. So if something's happening there, that's where it can't be. Y'all look like you're freezing. And I'm sorry. Go over there and turn it up a little bit. So because the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right, then 0 is my point of discontinuity. I have a jump at x equals 0. So I am continuous on the interval negative infinity to 0 and from 0 to infinity. However, I do have a discontinuity at x equals 0, and it is a jump at this time. No, I was just telling you that. You just have to say that it's discontinuous. Let's see. How about this one? Continuous or not? Well, this one you probably know, or maybe. You have asymptotes where this is cotangent, which is 1 over tangent. So the asymptotes everywhere, what's 0? Right? If tangent is sine over cosine, cotangent is cosine over sine. So everywhere that sine is 0, I have an asymptote. So we're all is 0, and y'all were right. I just wanted you to be right. Every pi, right? So it's 0, because that's where sine is 0. At pi, at 2 pi. So in fact, this function has infinite discontinuities. Infinite discontinuities at x equals, how do I say it? K every k pi where k is an integer. I'm going to stop there. I think that's enough for today. We did several of these together. I'm going to have you do, don't have long, I'm sorry, I talked too long. 1 through 16. We're going to skip the writing ones, and 19 through 24. Most of these are just looking at the graph. 1 through 10 is what we just did. We just did 3 of those. But after that in 11, you're just looking at a graph. What's the limit as you come in from the left? What's the limit as you come in from the right? Does the limit exist? Is it continuous? Yes or no? Why? That kind of thing. So it shouldn't take you too long. It shouldn't be too bad.